Great. So in this case, to the Flash Prints workshop seminar today. I'm Rafael Martinez from AstroAI, and I am very happy to be here teaming up with the SMA team. For my own sake, I am going to assume you're all here because I was the speaker, not because of the pizza or the SMA, so that will help me feel better. Anyway, so I have a very generic title, and really what I'm here to do today is not to give you a very comprehensive description of transient physics. I think we have experts talking about that. I am not here to give you a very comprehensive description of machine learning algorithms. I think we also have lots of experts here that do it every Monday here at this time. But what I want to do is to try to bring the two worlds together and to do two audiences together in order to see how any experience that has been accumulated in time domain and machine learning, astrophysics, in other wavelength regimes can be used for sprints projects and for time domain with the SMA. So that is the goal. Several people whose work I'll mention are sitting in the audience, so I apologize if I say something wrong. But anyway, with that, let's get started. And so we're at the Sprints workshop, of course, and this is about a program to rapidly investigate novel time domain sources. And so, of course, it's natural to ask ourselves, why transients, why submillimeter, why rapidly, and why the heck am I giving this talk about machine learning? And, you know, maybe the most relevant one to answer is, well, I would say we love in a universe that we assume to be mostly static to see things changing rapidly and exploding and doing cataclysmic things. But also, I think there is interest, of course, in what kind of submillimeter and radio signatures we can get from those transients and in what timescales they take place so that we know what are the best strategies to do follow-up observations at submillimeter wavelengths. For these objects, here I just have some nice examples of things that are cool to look. This is a artist representation of a neutron star merger, and this here is an artist representation of a star being completely disrupted by the tidal forces of a supermassive or intermediate massive black hole. That's a tidal disruption event. So to put some context, this is a pretty old plot now that shows the wide range of variability in astrophysics. It's a little bit outdated, and of course, I'm not going to talk about most of what's here. I will be touching on a couple things, things related to cataclysmic events in stars like supernovae and things like that. I think this needs to be updated to include things like kilonova as well that result for things like collisions of neutron stars. And I will also touch on supermassive black holes and what I also consider some cataclysmic events that are not added to this diagram here, such as tidal disruption events and quasi-periodic eruptions. Let me get started with supernovae, and this is a diagram of, a relatively old diagram of characteristic time scale of the supernova as it reaches its peak and the peak luminosity. And, here's classical novae and, typical core collapse thermonuclear supernovae. And one thing to notice is that this upper right part of this plot used to be pretty empty. However, with the release of the recent surveys and other time domain strategies, it has now we have now detected a whole bunch of objects that are more in that region of this parameter space and of relevance. Two types of objects: super-luminous supernovae and fast blue, what is it that they're called? Fast blue optical transients, which are not blue in this diagram, but actually green. Of relevance is that they actually are above the limits that are set for the physics of both core collapse and thermonuclear supernovae, and therefore any sort of radioactive decay physics and propagation of the radiation through the ejecta of supernovae cannot fully account for the luminosities and timescales that we see here. Fast blue optical transients are exactly what their name says. They're very fast, they're very blue. In timescales, rise timescales of less than 10 days or so, with mostly thermal optical spectrum. Comparing, the light curves of typical supernovae with this sort of fast transients, we see that they raise pretty high up in luminosity, and they actually happen very, very fast. And so this is perhaps one of the most interesting targets for the upcoming surveys, Rubin, et cetera, to identify more of these objects and characterize what of these candidate energy sources could be the most relevant one for this type of transients. This is just a slide to motivate that question of how rapidly is it that we should follow up. These are typical light curves of some of those very luminous things. You see several things. You see, for example, undulations in the light curve that could be related to interaction of the expanding material with the previously existing circumstellar material. And you see that in time scales of maybe days or months, you see an evolution of the spectrum from pretty featureless into a rich spectrum, including many atomic species, as you see here. Also a nebular phase that is also observed in slow super-luminous supernova. So the point here is there is an evolution. This is indicating that something's happening as the supernova expands and interacts with the circumstellar medium. And possibly there are signatures in the radio and submillimeter that you also want to catch in that sort of time scale. One other aspect that is interesting of fast blue optical transients is that they are actually bright in radio and submillimeter energies. As you can see here, this is the time to the peak of the transients and a transient in the radio, and this is the luminosity compared to other supernovae and even super-luminous supernovae, which are typically not detected in the radio. These objects can be within the sensitivity limit of some of the relevant arrays and radio arrays. So it is certainly important that within those type of timescales, we are able to follow up these transients at submillimeter and radio observations. Let me move on to some other types of transients, maybe or maybe not related to supernova activity, but in the X-ray. We've been hearing a little bit this morning about X-ray. They're also fast, and when I say fast, I mean tens of milliseconds or so X-ray transients that have been detected mostly serendipitously in X-ray data catalogs, and they're usually raising very, very fast. They are typically associated with extragalactic sources. In the X-ray, they're spectrally soft. And we don't have a lot of those examples. We're still, exploring X-ray data sets to find more of these fast X-ray transients. They could be shock breakout emission in core collapse or supernova. They could be TDE related. If the accretor is an intermediate mass black hole, which is offset from the nucleus of the galaxy, because these objects are usually not associated with the nuclear regions of the galaxies, or they can be related to binary stars merger and the formation of a rapidly spinning magnetar. I like this plot very much from Fernandez and Merzer that was actually published before the detection of the first binary neutron star gravitational wave measurement, because it shows kind of how all the different processes in the merger of binary neutron stars, lead to different emission, and how the radio, for example, could have some presence in the precursor emission as the two objects orbit each other, and there's interaction between the orbiting objects and the magnetosphere of one of them. That also happens for the X-rays. But as there's coalescence of the two, there will be some accretion-powered emission in gamma rays, X-ray as well. And as neutrons start being captured by the atomic nuclei that are in the ejecta, that energy release in that process will heat up the material and produce the different colors of the kilonova over these sort of time scales. But also as that shocked ISM that is being shocked by the ejecta is reached by that shock, then a radio transient is also expected in timescales of months to years. So it nicely shows that. And the reason why we think some of these fast X-ray transients might be related to this accretion phase of the binary neutron star merger is because if you try to model the light curve of some of those objects, the models that explain this time evolution of the light curve in X-rays in terms of the spin down of the magnetar that forms, after the merger, sort of nicely reproduces the profile here, and therefore it's interesting to consider that as a potential explanation for fast X-ray transients. I am going to move on to more supermassive black hole related transients. Ricardo Arcodia sitting here, who's done a lot of work here with other people. This was also a serendipitous detection in galaxy GSN 069. By chance, we noticed while observing with XMM Newton these repeating bursts of X-ray emission that happened every few hours, I believe. And people immediately wonder, well, what is this? Why is this? What is happening to this X-ray source in the center of this galaxy that is doing that? And well, there's many potential explanations. I think one of the explanations for that, taking the lead, is the formation of an accretion disk, perhaps as a result of a tidal disruption event, and then a stellar mass, orbiting object that crosses that accretion disks and shock heats the material, producing these semi or quasi-periodic eruptions in regular intervals as it orbits. So this is another interesting type of transient that we are interested in studying. This is a plot of how the spectrum in the X-ray is mostly very, very soft. It remains soft even during the flare. Of course, there's a number of questions that you can answer, in terms of what's the circumnuclear region of this, in galaxies with a TDE, with a tidal disruption event looks like. How can you use that to constrain the physics of the accretion in these objects? And obviously how that relates to the canonical, view of AGNs, whether or not these objects are mostly detected in galaxies with a non-active AGN. So how does that relate to one another? It's important. Turns out, this is work by our former colleague Yvette Sandes, also has radio signatures, mostly, as you can see in this diagram, delayed. And you see some of the light curves of TDE-related objects, detected objects, for several observed objects in the radio. Well, synchrotron emission, as you know, these outflows interact with the circumstellar material, could be at the root of this emission. But 40 or 50% of optically selected TDEs produce this detected radio emission, and as you can see here, depending on where you are in this diagram, if you're talking of timescales of days to weeks. So this is another example of radio emission potentially helping constrain the models for what exactly happens in tidal disruption events. And now I am going to put on my AstroAI hat, and I'm going to talk to you about machine learning and what sort of things we can do that have been already done in other energy ranges to help characterize these transients. And there are at least 3 things that we'd like to do with these sort of transients. We want to do classification. We want to assign classes and labels to the different types of transients that we observe serendipitously. We want to do anomaly detection as well. We want to take a representation of all those light curves and find things that look different. In this case, for example, the TDEs, or that cluster together in a particular region of this representation space. And we can also take the approach of doing parameter inference. So how do you solve the inverse problem of taking noisy observations of a light curve and derive physical constraints, probabilistic physical constraints for the model parameters with uncertainties? All those three things can be done, have been done in time domain astrophysics across optical and infrared. We've been doing it with X-ray data sets as well, and I think it can certainly be done with radio observations as part of the SPRINTS program. In terms of classification, well, the idea is simple. You have a bunch of light curves. In this case, this was part of a competition we organized a long time ago now to try to use simulated LSST Rubin light curves and have the community try to classify them across different types, not only supernova-like, which these early classifiers were so biased towards supernova classification, but other types of stellar and galactic flares, et cetera. And initially, the approach to providing accurate classifications across different classes was based on manually extracting features from the light curve. So you would take a light curve and you would sort of measure the mean and the kurtosis and the skewness and any linear trends, and you would use that as the input to, now almost forgotten machine learning approaches like, oops, what happened? I think I moved the laptop a little bit and it went away. Apologies, sorry. Like random forests, ensemble methods this was basically an ensemble of decision trees that would give you, in a non-necessarily probabilistic way, labels for each of those objects that you wanted to classify. And there's, of course, a lot of work related to the plastic and elastic challenges that use simulated light curves, but now we have the real data, so this is now actively being done. But as AI advanced, there was no need anymore to manually extract those features because you could not know in advance which of those features could be more informative for your downstream task. And so people have started using neural networks. And here is Dan Muthukrishna somewhere who's done some of this work as well, who's an AstroAI fellow now. And basically, why not letting a neural network learn the relevant features for a particular downstream task of classification of anomaly detection? So you can just pass on your light curve, your input data. You don't need to care about computing kurtosis or skewness or anything. Just let a set of layers of neural networks, in this case, a recurrent neural network, to learn those features automatically so that then you can. Oh, is it because I'm stepping on this thing? I don't know. Sorry, guys. Hopefully I'll be back. Otherwise, I might need to sing, as I said. It's actually not coming back. So I don't know what's going on. Sorry. Does anyone know here what? Oh, there. Don't move. Stay right there. Okay. So anyway, so these recurrent neural networks, for example, are neural networks that are based on persistence, on memory. So the particular state of a sequence of a time series, for example, depends on the previous state, the previous point in the light curve, and can generate representations that then you can reduce in dimensionality to look for interesting things or to classify. So, for example, here you see that these AGNs are particularly coming off from all these other supernova-like light curves. So we can now learn features automatically for a particular downstream task of interest, be it classification or anomaly detection, for example. There's many other approaches for this kind of exercise of taking input like time series inputs and turn it into a representation that you can use for those. Happy to talk about that with others. There's, however, issues with this approach. There's something called the vanishing gradient problem, because when you train a neural network, you need to compute derivatives in order to update the parameters of the neural network, and sometimes those derivatives are very small. So you end up multiplying very small numbers, and that leads to numerical errors. So these approaches can be problematic. Light curves can also be irregularly sampled, heteroscedastic, et cetera. So before I go to one possible solution of that, I'll mention another work by Nan that uses another autoregressive approach using convolutional neural networks that has different dilation between elements of the neural network, again, to create a representation that can be used, again, for exploring that representation of the space, but also to predict the next, depending on how many points you're considering along the light curve, you can also predict the next few points or the next point in a sort of sequential way, and classify. And also, depending on how much you deviate from the expected value of that light curve, you can also find anomalies. So there's many ways of doing this. But I was saying, because of all those problems that these recurrent neural networks, transformers are rapidly sort of transforming the landscape. And transformers are the same type of neural network that large language models use. They are basically linear neural networks that process sequential data. And the difference is that this is not based in persistence anymore, as in recurrent neural networks that rely on the memory of knowing what was happening in the past. It relies on something called attention. So a transformer computes the amount of attention that each element of a sequence should be paying to other elements of the sequence in order to make a particular prediction. So in the case of language, it's like how much attention should a particular word in a sentence be paying to other words in the sentence. But in the case of spectra or light curves, it can be, how does this spectral line emission, is affected by something that happens in the continuum at higher energies, for example, things like that. And because they are trained in a way that takes the full time series at once, that helps in the training, and it's been sort of revolutionary in the way we deal with sequential inputs. Just very quickly, for those of you who've been wondering what is this transformer business, it's just a neural network that will take vector representations of elements of the sequence and pass them through some linear transformations that will create three different learnable vectors, query, key, and value. You can think of that as a query in a library or something like that. You have a particular element or word you're looking for, you query it against an index of different meanings or information, and then you weight the dot product between those two things by the value that element of the sequence actually has. And that will give you a score, a representation of that element of the sequence for the particular downstream task that you're trying to solve. And you can then, again, use this representation to put it into a 2D plot and see if there's any anomalies or things like that. But that's what the mechanism behind transformers is. Now, this is one of the earlier uses of transformers in astronomy, time domain astronomy. This was basically trying to do the same thing that transformers do with language, but with magnitudes and observation times of photometric points in light curves, doing some positional encoding, which is basically telling it the order at which the elements are being presented, do some layers of that attention mechanism I just described, create a representation, and then use that representation to, instead of the light curve itself, to do some classification downstream task. And as you can see here in these plots, by the way, the neural network is trained by hiding some of the elements of the sequence at each training step and having the neural network try to guess what those things that you were hiding were. And as you can see here, when you sort of beef up a recurrent neural network or a simple neural network that is fully connected, but you beef it up with this attention mechanism, you get better performances in the classification task, and therefore you sort of try to use something based on this attention mechanism instead for the downstream tasks. Okay, let me see. Okay, I still have time. I'm going to give you another example of, and I hope I'll leave time at the end for discussion, but I'm gonna switch to something again in the X-ray, and we have large serendipitous catalogs of X-ray sources, and we are interested in finding, for example, these fast X-ray transients, or those quasi-periodic eruptions that I was talking about before. And working with a student early on in the AstroAI collaboration, Steven Dillman, who's now at Stanford, we came up with this representation learning approach to find transients in X-ray data sets. And basically, the trick here is that X-rays are, complicated in a way, because they're not just streams of like photometric points, continuous values. These are actually individual X-ray photons being recorded by the detector. And so in order to create a light curve, you basically need to like bin it in a particular way, et cetera, et cetera. So what we ended up doing here was to take those event lists, which are basically photon recordings with a time of arrival and an energy carried by each of the photons, and just creating 2D histograms of arrival times and energy. So something like a dip would look like this. Across energies, something like a flare would look like this. And we pass this input to a neural network called an autoencoder. That is basically something that takes your input, sort of compresses it into a small, small dimension representation, and then it takes that representation and attempts to reconstruct the input. So that is a way of compressing information by making sure that the information you have in this so-called latent space has enough information to account for the reconstruction of the object. And then you can take this latent representation, further reduce it in dimensionality, and you can look at whether the known objects that you're looking for, happen to live in a particular region of this space. And in fact, what Stephen found was that, well, first of all, it sort of codifies things like the hardness ratio. This is a diagnostic for the spectral shape of the object. But he also found that a lot of the many sort of transients, like the ones I've been talking about, including also a dip by Rosanne Di Stefano and collaborators that was a candidate for an exoplanet transit in front of an X-ray source, sort of live in very particular regions of this diagram, which allowed us to look for other potential candidates of these sort of objects. These are some examples of the light curves that we found through that. And Stephen found this interesting transient in the Magellanic Cloud. We think it's in the Magellanic Cloud. We don't have an optical counterpart to actually be sure, but it's very fast. You see it here in the light curve. It's relatively hard, as opposed to most of the fast X-ray transients that have been found, which made us believe this is probably a type 1 burst, thermonuclear explosion in the surface of a neutron star. We don't know yet because we haven't been able to follow it up, but maybe the SMA will know. I don't know, who knows? Anyway, okay, I'm going to move quickly into parameter inference. And this is basically, as I described, the inverse problem of taking some noisy data and try to derive probabilistic posteriors for the parameters, physical parameters of your model. So basically, we do that with probabilistic neural networks. Basically, these are all density estimators. They want to estimate the joint probability distribution of something. And that something can be data, in 2 different dimensions of the data, or they can also be data in a simulated setting where you have simulated data with noise. This probability distribution can also describe the probability of those noisy data together with the parameters that led to that. And so you have a joint space of the parameters and the data. And depending on how you condition this, you can find either likelihoods. So given these parameters, what is my data looking like? Or posteriors for the parameters if you condition the other way around. And we do that with probabilistic neural networks, like normalizing flows. This is variational inference. And this is basically trying to derive the shape of this posterior by starting with a very simple distribution, something like a Gaussian, for example, and then transform this Gaussian with a number of invertible transformations. You start transforming it with these functions, and then you get finally something that looks like your posterior, and then you train a neural network to go the other way around. And in that way, you're able to learn sort of the shape of those posteriors. You optimize the neural networks until you recover the form of each posterior. This can be done as an alternative, as a faster alternative to things like Bayesian inference with MCMC. But you need to make sure that you're well calibrated, that your normalizing flow is not like overconfident, things like that. But anyway, you can do that to to basically recover, as I said, for example, the likelihood of the data, or you can recover the posterior. You can get uncertainties for the parameters of the model that you're trying to test, starting from noisy data using this sort of neural networks. And all that you have to do is you train your neural network to maximize the likelihood of the data. That's what you do. Anyway, so people have done that. Also, Edgar Vidal at Tufts, for example, working with some colleagues, former colleagues of ours, Alex Galeano, Carol Cuesta Lazaro, they've looked into the problem precisely of what is the source of some particularly luminous supernova, interaction with circumstellar material, or that plus magnetar, rapidly spinning magnetar. And they've done a similar approach to normalizing flows. It's not exactly normalizing flows. It's something called flow matching, which is also a probabilistic algorithm that will allow you to derive a posterior probability distribution. And they applied this by getting posteriors for different types of models for the same data. And as you can see here, the inclusion of a magnetar model significantly affects the precision of your posteriors, but also allows you to generate posterior samples for the light curves you're simulating. And again, it can also be used as a way to find anomalies, just as I said before, by looking at how far your posteriors are, based on the model you're considering from the actual data. So when you see deviations for that, you can assume that that could be an interesting anomaly. And this also creates a representation of those light curves that you can then cluster and try to see if they can be useful to find things like tidal disruption events that can do. This is all with simulated data, of course, but it certainly presents a way in which you can use probabilistic machine learning on sequences of astronomical observations to infer physical parameters and at the same time do anomaly detection. All right, I am going to start wrapping up so that we can have a little bit of discussion or more pizza, whatever you feel like. But I want to tell you a little bit about what sort of things are the things that we could potentially do with the SMA. And I'm going to talk about three aspects. One is, of course, so suppose you want to turn and I apologize for my ignorance about how the SMA exactly works. But suppose you want to turn it into a follow-up machine for alerts from Rubin, for example, given the timescales I've been discussing for different types of transients, et cetera, et cetera. So I think in terms of transient alert prioritization, the first thing you would want to do is, have a very lightweighted sort of binary classifier. Is this actually worth following up with the SMA at all or not? What is where in the sky is this object? What sort of redshift it has? What is the estimated flux for it? Is it worth following it up or not? Then you could go into a multi-class classifier, trying to see if any of the transients of the alerts are particularly relevant for the particular science that you're interested on. This stage could in principle be designed by the Sprints team, for example, or existing brokers that have been attached to the Rubin infrastructure that do precisely that, take alerts, pass them through classifiers in order to issue these alerts. That can be incorporated into this, maybe with a little bit of additional flavor for SMA transients. And then you would get a score, right? With the context, weather conditions, et cetera, and that would give you a way to prioritize from the many, how many alerts per night in the Rubin, who knows that? 10 million. 10 million? Well, this is gonna tell you exactly which ones to look. Anyway, so that's one thing. The other thing has to do with automatic observing and scheduling. Of course, you would want to, decide how to follow up these objects once you've decided which ones or when to look, when not to look, for how long to look. So this can be framed, for example, in terms of a Markov decision process, where there's basically an agent that is your scheduling neural network. There's a state. So what is your current, in Markov processes, you only sort of depend on your current state to know what's going to happen next. So that state can be, array configuration, something about the sky, or something specific about the alert. You can take some actions based on the information you currently have. And then you need a reward, right? Because this is ideally, this would be trained with a deep reinforcement learning framework, which does not work by assigning labels as giving the neural network the truth of the time, but just giving the neural network the outcome of a particular action and deciding whether the outcome was positive or negative. And so the neural network sort of interacts with the environment and decides what's the best approach to take next. Of course, this would be difficult to train on real data because you would need lots of data. Perhaps building a digital twin to the SMA on which you could sort of simulate these observations and try to train an object that decides on the schedule will be a good way. And finally, mining existing archives. I mentioned, for example, that some of the transients that I discussed could have some precursor emission in the radio and the X-ray. So maybe even before there's a transient, you can find for the typical signatures of a precursor in existing data of the SMA. And some of the techniques I've been discussing, unsupervised clustering, take things that you don't know what they are and organize them in a certain way so that you can separate different types of things. You can do self-supervised representation learning, so pass existing data to a neural network that sort of learns what features of those data, even visibility data, and see what sort of aspects of those data sets are relevant for time domain. Or this is something that has certainly been done for projects like the Event Horizon Telescope, find deep learning analogs for reconstruction of the image or the cleaning process. And this is just, I crucially left aside a very relevant type of object for this talk, which is fast radio bursts. And I don't know if Liam would be here or not, but anyway, this is a clustering exercise with light curves from fast radio bursts, where they sort of try to find different clusters based on those light curves for 8 different observations of the fast radio burst and see how those clusters were represented in terms of fluence and peak frequency, et cetera, et cetera. So similar exercises can be attempted with different types of transients in order to characterize them. I think that is what I have for you today. I will leave you with this. There's a lot of things we can do with radio and transients. We can learn a lot about populations of binary stars or supermassive black holes. There are some timescales of relevance that could potentially be informative for a way in which the SMA could follow up these objects. And crucially, there's an existing set of tools that has already been designed in time domain across other energies that we could adapt or think about how they would adapt for the submillimeter range. And finally, there's a few things other than just science that machine learning could help you with, including prioritizing follow-up targets and scheduling observations. And with that, I'll open it for questions. Thank you very much. Ooh, pizza. I guess I'm chairing the session. So are there any questions for Rafael? Yes, Neta.
Very nice presentation of all the methodologies. I have, I think this is maybe the first time I see this probabilistic approach to machine learning and it's very usual. I was wondering if there is a way of about the comparison on MCMC versus machine learning on this parameter space for your case. Because there was like magnetar, no magnetar.
Yeah.
The distributions are nice, but
right.
Explanation of those methods.
For that particular work, I don't know. I think provided that your MCMC has been done right and has converged, MCMC samples are always a very good ground truth for how well calibrated your probabilistic posteriors are that come from machine learning algorithms. Unfortunately, if you have a many parameter problem, do this MCMC thing can be very computationally expensive. So there are ways to calibrate, how well, calibrate your posterior is by looking at things like how often, that's your ground truth. If you run the experiments many times, how often your ground truth actually falls, in the corresponding, sigma levels of your probability. And so you can calibrate it that way. We have done this for an X-ray relevant task, which is PILAB, so trying to derive physical parameters from piled up observations in X-ray data. And we show that in the case where it's PILAB dominated, our normalizing flow approach gives much better constraints on the actual parameters, because you're using more information instead of only the outskirts of the PSF. And in the case where there's no PILAB, the MCMC and the normalizing flow converge to the same time of distribution, except that the normalizing flow does it much faster. But for that work, I don't specifically know exactly what those guys did. Yeah. Yes.
So a question that I have is, can you say a bit more about the masks that you used, and if that has any
About the
masks that you've used, and how that may influence different types of transits?
You mean in the way these transformers are trained by masking? Well, that's a very general question. Most transformers are trained. Basically, you're training a transformer for it to learn the sequence, and what is the sort of distribution of probable sequences that you can observe. So there's several ways to do that. A lot of transformers are trained on what's so-called next token prediction, which is given this many elements of the sequence, tell me which element comes next. But some, including that transformer that I showed, the AstroAI transformer, was trained on a masking task where you just take away. And this is a relevant question. I think it's a question also for the machine learning community. How do you best train? What are what are the hyperparameters of how exactly you train your neural network impact your downstream task? And we have been doing work here about that, not necessarily in the case of Likers yet. Maybe some people have. But in terms of what is the best way to actually train a particular transformer model in order to get the best performance possible in that. So I think it is a relevant question to talk about what training strategies for these transformers you will want to use in order to have the best outcomes for particular downstream task in radio Likers.
Sorry, the reason I was asking is this. There's a whole question of what comes next can be used as an approach to also have some sort of forecasting built into these classifications, and then using that to inform sprints or whatever type of thing you're using. Say, okay, at this point we expect these that.
Yeah, I think forecasting is one of the most natural tasks for these sort of systems. What comes in the future, and how you can use transformers in a sort of autoregressive way to predict the future in different timescales. And I'm sure there's people here, like Dan or others. We're also doing with the heliophysicists now. We're trying to incorporate these autoregressive sort of approaches in order to predict the future. So that's obviously one of the most natural tasks for these systems. Yeah. Who was next? Sorry.
Yeah.
Oh, I think it was there. Yeah.
So I'm not sure I understand correctly why I got the right impression. When you show some examples, I think at some point you start with random forest. You sound like it's kind of out of fashion, and then you're doing transformer, and then you show the oral kind of example. As a non-expert in machine learning, when I try to apply some of these techniques to my problem, I'm kind of overwhelmed by all these different methods. How do you see the landscape? If something is going out of fashion, so let's say random forest was going out of fashion, then you guys don't use it anymore? How does it work out?
I mean, I think the community has a tendency to do that, yes. So I think everyone now wants to do foundation models. Everyone wants to do transformers because that's kind of what's there, right? I personally think random forests can be great classifiers, for example, and I would certainly encourage people to try something like that. It depends a little bit on, how complex your space, if the space you're trying to explore is very non-linear, right? Maybe random forests are not the best choice. But for certain particular sets of problems, they can be very useful. And I am certainly not trying to discourage anyone from using, more traditional machine learning methods, in particular because they can be way more interpretable than the things that I described here. And I think it's important for us to keep in mind that we want to know what these representations mean before we actually publish any results on them. And so, no, I don't. Well, yes, I've been using a lot of transformers lately, but no, it's not intentionally.
Going back to the forecasting point, I think one of the things that would be really valuable with sprints in the long term, I don't know how long it will take to get there, is classifiers that tell us whether to keep us, we get our first 10 minutes, we do a rapid response, we get 10 minutes of data, we rapidly reduce that. And we need to know, do we keep looking at this source or do we go back to what we were doing before? Or do we follow up the next event in the queue? So a forecasting classifier can say, you'll learn something scientifically valuable by keep observing.
Yeah.
Or not.
Right. No, yeah. I mean, I think the timescales and specific setup of the observation is different from like optical service. But you can talk to people like Dan who've been thinking about how to do classification on the fly and when to follow up spectroscopically, for example, if you're looking at an optical light curve and it suddenly deviates from what you expect. So I think a lot of those approaches for the SMA in terms of, yes, do I switch to the next source or do I stay on source are relevant. And I think this should be an opportunity for us to discuss precisely how those things could be adapted and, leverage from the expertise of people working in optical service.
We at least get spectroscopy for free.
Right.
I'm wondering about spectral information. If you just think about 5 different bands, optical bands that are being imaged, every night. So essentially you have light curves in different bands, and you have spectral information, which should be really useful for classification too, but you didn't talk too much about that. Is that kind of information easily or automatically included in the classification of light curves?
Yes. I guess the reason why I don't think separately of light curves and spectra is because I've been an X-ray astronomer for too long now, and I only have a bunch of photons. But but certainly I think yes. So many of those methods are can be adapted to spectra, but more importantly, I think incorporating doing multi-model studies, taking the light curve photometry and the spectral information is definitely super relevant. And here, people like Ashley Villar's group have been doing exactly that, looking at multi-model data sets, and others in the AstroAI group to do better classification when different pieces of information are available about the source, and also doing it in an automatic way. So, of course, spectra, at least in the optical, are much less common. So one of the things you want to do, and that these probabilistic methods can help you do, is try to predict spectral properties from what you have available for most sources, which is photometry. And that's something that people have been trying to do, in some cases quite successfully. Thank you.
Any other questions?
Yeah, I have been. There's none. Any online questions?
I will encourage the sprints team to talk to the people in the AstroAI team about specific things. We have, I mentioned a couple of names during my talk, but we're from the government and we're here to help. So come talk to us. All right, thank you. Thank you very much.
We're gonna see for the 5 minute break. Thank you so much
Me quedé en el molde porque creí que 100 chorros de luz tenía.